Hello everyone, I'm Wanli, coming from Jimei University. Our work is Propagation Characteristics of LoRa-based wireless communication and steel ship cabin. The main engine is the power center of a ship. Monitoring the equipment state of the ship cabin during navigation is of great significance to the stability and safety of the ship's operations. With the traditional method, the data transmission in the cabin adopt wired communication using feedback technology. The cost of marine wired communication cable layout in a ship is relatively high, and it takes a very long period for construction. Therefore, wireless sensor network and Internet of Things solutions are adopted for ship application. For the large-scale ship with more complex environment, which contains abundance of reflecting and diffracting elements, it needs communication technology with longer transmission distance, longer battery life, and better pass-through ability. Low-power wide area network has received much attention and development due to its significant advantage in long-distance transmission and low end-node power consumption. Feasibility of LoRa technique applying for indoor environment of ship has also been verified by researchers. So far, researches on application of LoRa technology on ship were mostly focused on experimental tests, and the installation location of the access point was mainly based on the experience of designers, which would greatly lessen the construction cycle and demand lots of resources. Establishing accurate indoor path loss model and predicting the propagation characteristics of wireless signal according to the propagation environment would greatly reduce the cost of network construction and would also be of great significance to maintain communication stability. In this work, a three-dimensional ray tracing model of LoRa-based wave propagation in ship cabin was established, and multipath propagation prediction was carried on and receiving power was calculated. Experimental result for measuring in real ship was compared with the simulation, and the main influence of ship cabin spatial factors on wave propagation was discussed. Then, important guidance was given for communication link design of LoRa technology-based wireless sensor network in ship. The ray tracing method was adopted in this work. By ray tracing method, the electromagnetic wave propagation characteristics could be analyzed based on the principle of geometric optics. For the diffraction caused by the obstacle, it emits a ray from the transmitting antenna Tx, and then checks the ray to see if it correlates with the surface of an obstacle and is received by the receiving antenna Rx. Then calculate the power or electric field associated with the ray to contribute to the receiving point. The average received power of total propagation path Pn is as follows. MV Yude, a cargo training ship, was chosen for this study. It is the largest training vessel in the world and has been used for seafaring education, training, and scientific research, as well as carrying bulk cargo. The main engine room is located at the rear of the ship, and here is the specifications of the ship. To examine how the equipment affects the wireless signal propagation, the diesel engine is selected and modeled in this simulation, as it is the largest equipment obstacle for signal. The established model is shown in the figure. The bottom platform has set wire cabinet at its rear part. The middle platform has auxiliary machine at its rear part and corridor around the diesel engine, and the control room is located in the top. Platform with a corridor around the engine and pipes. Some detailed interior construction is ignored and simplified. The arrangement of the initial transmitter Tx and the receiver Rx is shown in the figure. Tx is placed at a height of 1 meter above floor level on the bottom platform of the cabin, and Rx is moving away from the Tx and is set at various routes around the diesel engine. RS1 is set at the bottom platform of engine room, which is length route B here. RX2 and RX3 are set at the middle platform, which is 5 meter height distance from the bottom one and is length route M. RS4 is set at the top platform, which is 9.8 meter height distance from the middle one, and it is length route T. The receiver points set at each route are various, where route B has 25 receiver points, route M has 22 points, and route T has 50 points. The received power values are measured every 1 meter from the starting point to the end point of each route by the receiver. The experimental measurement is taken at the main engine room of MV Yude. The experimental equipment includes LoRa communication node, a small computer with serial port program, as well as a tripod used for adjusting measuring the receiver. The omnidirectional and monopole copper rod antennas working with vertically polarized mode are used as the stationary transmitter and roaming receiver. The overall height is 205 mm with effective length 175 mm. Thus, the monitoring is done with 433 million Hz frequency at the measuring point, which are selected alongside the same path in simulation. And here shows The comparison of experimental and simulated results of the root B, the root M, and the root T. From the comparison, here comes some conclusion. Either the simulation or experimental analysis indicate that the signal propagation in the steel ship cabin is very different from the propagation in the ordinary buildings, which is strongly affected by the multipath effect. Although large obstacles exist in cabin environment, the wireless signal transmission system using LoRa technology can still meet the requirement with suitable deployment. Deploying a base station near the glass window and avoiding being near the back of the main switchboard in the control room could help to establish good communication link even from the bottom platform of the diesel engine in cabin. The analysis validates that the simulation research based on ray tracing method could help to provide guidance for designing wireless sensor network with LoRa band. It could clearly show the areas which are prone to produce impact of multipath fading on signal propagation and need to be avoided, as well as the suitable location which would enhance the signal strength. For example, the receivers are suggested to locate it near the staircases, which would be helpful for the transmission, but avoid the region beneath the chimney of diesel engine or in the diagonal position of transmitter, which will reduce the received power. It should be pointed out that the amplitude variation of experimental test is much bigger than the simulated result. That is mainly because the complexity of the real cabin environment with a lot of machinery equipment as well as metal racks, pipes, and grooves. Nonetheless, it shows similarity in signal transmission trend along the measurement path given the relative roughness of the ship cabin models. The special cabin environment is much more different from the common building interior space. Hence, some special phenomenon is appeared in the signal transmission characteristics. Therefore, from our work, it can be seen LoRa-based wireless communication could be recommended for ship cabin applications, and using the ray tracing model combined with few on-site measurements to evaluate the signal propagation will be less time-intensive and less costly. For the world-scale ship, the cabin environment will cause the wireless signal to fade through complex phenomena such as reflection, transmission, and scattering, and so on. Thus, the investigation of the influence of the equipment on wireless signal transmission is important. The deployment of wireless sensor network and chip application traditionally relies on human experience and the lack of theoretical analysis. And our work is to do this field. The important guidance given for communication link design of actual LoRa network and chip will be helpful in the real application. That's all. The end. Thank you, everyone.